going to look at a problem here and analyze it using several different decision rules from the area known as decision theory or decision analysis. So at the top here, suppose we have a state government that's going to build a new exit on a major highway at one of two possible locations. And we would like to purchase land with the hope of building a hotel at the exit. Now, unfortunately, we have no idea which exit they're going to choose. So we have to make choices before we have that information. And so in the first table, there are a number of different outcomes depending on what the state decides. So let's look here first at this column here. We have two possible locations that we'll call exit A and exit B. And if we were to currently purchase the land at location A, suppose that represents millions, so that'd be $19 million. Now, if the hotel and exit are built at this location, in other words, if we guess correctly and they do end up building their exit at location A, the present value of the future returns would be $30 million. On the other hand, if the state does not build an exit there, the best we can do is to get rid of the land for only $7 million. And why would the 7 be so much less than the 19? Well, you can imagine in the real world, if there's been an announcement about a possible exit, that there'd be some speculation which would drive the price of the land up. On the other hand, if it turns out that the exit's not built there, then you have land that is going more for a realistic price rather than the inflated price. So in this column here, column B, if we currently purchased the land, it would be $11 million. If we're lucky and we purchase the land where the exit ends up being built, we can get present value of future returns being $24 million. On the other hand, get rid of the land at $5 million if it turns out the exit isn't built there. So from this information, we're going to build what's called a payoff matrix for this hotel and exit problem. Now with decision problems, we have what are called alternatives and we have what are called states of nature. The alternatives are our choices as decision makers. So as decision makers, we have four alternatives. We could decide to purchase land at location A or B. We could actually buy both of them, or we could just pass and buy neither property. So these are our alternatives. The states of nature simply mean the things that are outside of our control. It's up to the state to build the exit, and all we know is that there are two of them, A and B. We don't have any further information, no probability on this. Now, if we do have reason to have probabilities, for instance, there's a 75% chance that they'll build the exit at A, that will require methods which are not covered in this video. So here we just have absolute uncertainty. So let's fill in these here, these various spaces, okay? So first of all, the land is purchased at A, and I'll click in this cell here. So we purchased the land at A. So let's do this. Let's first put in what we pay to buy A. It would be $19 million. So I'm going to do an equal sign, and because that $19 million is a payment, I'm going to put a minus in front of it. And then I'll just click on the 19. Okay, so we spent the $19 million, and we'll either get $30 million or $7 million back. So we have to look at this side of it. This is saying that the exit was built at location A. So we bought at A, and they decided to build at A. So in this case, we did well. We'll get the $30 million in returns. So that would be a net result. Spend 19 and then get 30, and that result would be 11. Let's go across here because it'll start the same way. This row here still says we purchased A, so our purchase price would be negative. we would again click on the 19. And now let's figure out our return, either 30 or 7. Well, we bought at A, but they decided on B, so we end up having sort of made the wrong guess here. Best we can do is to sell that land for $7 million. So we come out behind. Let's do the exact same logic for the next row. So here we purchase the land at B. So let's start out with our purchase. So that would be a minus. We purchase land at B. That purchase price is $11 million. Click on that. And let's figure out, did we do well, get 24? Did we not do so well and get 5? Well, we purchased B, and here we're doing that the exit was built at A, so unlucky here. We would sell the land for $5 million, and that would happen, as you can see, at a loss here. And same logic here. For this sale, we purchased, it says land purchased at B, that would be our minus $11 million. But this time we nailed it right. We purchased at B. They did choose B, so we come out getting nice future returns for that. The next row, well, this will be sort of the same idea, but we'll have to be real careful with it. We purchase both of them here. Okay. So let me do a minus sign, and since we're going to have two purchases, I'll just put them in parentheses. So we would have both the 19 plus the 11. And now close your parenthesis there. Okay? Negative, so an expenditure. Now let's figure out what we get for this. So we'd have a plus sign. Now remember, we're doing this cell here. So with this cell here, they chose to build the exit at A. So we do real well on our purchase of lot A, but not so well at B. So let's see, we're a winner at A, that would be the 30. But the B property we bought will not have an exit built at it, so that would be the 5. And finally, the last one, it's going to start out the same. We're going to have a minus. We purchase both, so the cells containing the 19 and the 11 there. So that we spent that much, and let's see how we came out here. Now we have both properties, but they chose to build at B. So our property at A has to be sold at a loss, but since they built at B, that's where we come out having valuable property. And let's see what we have here. Okay, a 1. Finally, if we buy neither, we're just plain not in the game here, and those would be zeros. It's important to include that possibility in a payoff matrix, because sometimes the best choice is, in fact, to not get in the game, if you just don't feel you have a good set of choices. All right, the first rule I'm going to show you is called the Maximax. To do that, we're going to add a column here for our maximum values. Now, what you would do here is you'd look at each pair and you would just write down the maximum here. You know, so for instance, with the 5 and the 1, the max would be 5. Let's use Excel. A way for me to show you a simple but useful command. It's the max command in Excel. So start type on the word, and you see here you have a max you can choose. And what you do is you just choose the two numbers that you want to find the max of. And of course 11 is bigger than negative 12. And you can copy that down. Now what the Maximax criterion does is, out of those maximums, you find the maximum. Now honestly, look, we could just look at those, right? 11, 13, 5, and 0. The max of those maximums would be 13. Let's use Excel to do it though, which would be helpful if you had a really big matrix. So let's choose the max again, but this time we want the max of these 4 previous maxes, and we would get, like I said, 13 is the biggest of those. Okay, so Maximax literally stands for find the maximum of the maximums. Well, our alternative that we would choose based on this, then, we would just look at the find the 13 there, and that corresponds to purchasing land at location B. Okay, so by B. Now you can think of the Maximax criterion as being sort of an optimist choice. Optimist figures, hey, what could go wrong? I'm lucky. So kind of going for broke, going for the gold. For many people, that's too risky. And they might, a more conservative person might want to reject the Maximax solution. So there's another procedure which is called the maximin. So with maximin, we first would do a min column, and then we'll do the max of that min column. Now the max command was real simple, wasn't it? Min command is just as simple. It's just min, gives a minimum. So we select the 11 and the negative 12 there. Oh, excuse me. We select that. So the 11 and the negative 12. And notice instead of giving the larger, it gives a smaller of the two. Similarly, that can be copied down. And so the maximin, let's work it out. The maximin will be found by taking the maximum of these minimums that we just found here. And that would give us a 1, and so we could look at this min column and see what the 1 corresponded to. It would be to buy A and B. Let's just pause for a second here, and let's kind of look at the psychology which is going into that one. If we buy land at A, we could make a lot of money, 11 million. We could also lose a lot of money, 12 million, right? So there's a big range there. With B, we could lose, in my opinion, a lot of money, 6 million. We could make 13 million. But when we look at A and B here, look, the best you can do is not as good as the best up here. It's only 5 million. But the worst you can do is to make 1 million. So it's kind of looking at it more from the pessimistic side. What if the worst happens? How can I maximize that worst outcome? And, clearly making 1 million is, well, it's not bad, right? So that's what the maximin does. Maximax is the optimist. Maximin is more the pessimist. Of course, depending on your mindset. Some people would say the Maximax is sort of the foolish person's decision, and maximin is maybe the scaredy cat, the one who's not willing to take any risk. I would recommend that you do think about some of your own decision-making processes and think about it. Maybe that in certain areas, some people in sports maybe would do the Maximax. Some people in their personal investments might do maximin. You obviously in real life aren't used to thinking about it in terms of matrices, but I have a hunch that Maximax and maximin do reflect, very likely to reflect your own thinking. Now, we're going to look at a third rule, which is sort of a compromise. It's a different way of looking at it. And in some, but not all cases, the third rule I'm going to show you may give you a choice that's even different from the alternatives that we selected here. To do this, we have to use the idea of regret. Now, if you're a business major, you probably have heard regret referred to as opportunity loss. look at it this way. Let's suppose you're on a game show and there are two doors, and the host tells you behind one door is $1,000 and behind the other door is $10,000. So you go and you open a door, and what do you get? $1,000. Well, you should be happy. You just got $1,000 free, but it doesn't probably take too long before you're thinking, yeah, I got $1,000, but I sure wished I'd chosen the other one, because 10,000 would be 9,000 more. Well, that 9,000 more, that's what we refer to as regret. So regret is the difference between the best solution minus your solution. So here's how we can work out regret pretty easily using Excel here. In order to do the regret matrix, we'll be using the payoff matrix to do our calculations. So click here in the first cell, the regret matrix corresponding with A and A. Here's what we'll do. First off, we'll do a max function, and we will do the max of this column here. Okay? So one way of looking at it is if they were to build the exit at A, the best you could have done would be if you'd purchased land there at A, and gotten 11 million. So we take that max and then we subtract away that first cell. And we hit enter, and let's look at it. It's 0. Why? Well, because if they built the exit at A, the best thing that could have happened to you would have been to have earned 11 million. You did earn 11 million, so you have no regret whatsoever in that case. These other ones there will be a regret because it's not as good as having earned the 11. Now we could drag this formula down. Before we do, we better see if there's anything we need to make absolute. Notice we want the second element of the formula to change, but the D29 through D32, I don't want that to change, so I'll make that absolute reference. And once I do that, then I can go and copy this down. So these are our regrets. Like at this point, look at the very last number of the payoff matrix. Person's going, I didn't make anything. If I'd been willing to take a chance, I could have earned 11. So there's an $11 million regret there. We'll do the same thing over here in the second column of the regret matrix. So in that first row there, do your max of the second column. Let's make it absolute while we're at it. F4 is a shortcut to make things absolute. Close your parenthesis and then subtract the first entry. And we get a $25 million regret. And let's copy it down. Notice the 0 regret comes right here, which makes sense. You could have made 13 million and you did. So absolutely no regret. Now, the decision rule, what used with regret, is called the minimax regret rule. So to do that, we'll go back to our regret matrix, and we'll first work out a maximum column, and then we will go and minimize it. So first let's do the maximum column, equals max. We grab the first two values. 25 is the biggest, and we go and we copy this down. And so over here, let's do our minimax regret. So this is a maximum regret, and let's minimize it. So equals min. Select those max regret is what we're selecting. And we have there a value of 12. As I said, sometimes this rule will give you a different alternative to choose, but let's see, what did 12 correspond to? Well, in this example, 12 also gives us A and B. I suppose you could argue that, well, since 2 of the 3 rules gave you the same answer, that maybe that lends some weight to that rule, but of quite honestly, you know, there's a psychological element in here, and some people will reason differently about it. But I think it's kind of nice to be able to compare different rules. All right, so in another video, I'm going to show how to handle decision problems where we're not totally in the dark. As I said earlier, suppose we've got a pretty good hunch that there's a 75% chance that they're going to go with exit A. That additional information will give us a more refined way of making our decision. All right, signing out. Good luck.